for accepting our invitation. So it's a pleasure to have you here with us. So Anna from Warwick Business School. Anna will present credit conditions on the asymmetric effects of monetary policy shocks. So you have around 1 hour, and we might, as I explained before, we might interrupt with questions and yeah.
Yes, so I'll be happy to answer questions because otherwise it's very boring just me talking. So thank you
Fantastic.
for the invitation. I'm happy
Thank you
to
very
talk
much.
about my
Excellent.
work. So this work is joint with Andrea Carreiro and Massimiliano Marcellino. So let me explain the main motivation here of
Sorry,
this
I
project.
should announce, sorry to interrupt, Anna,
Mhm.
that we are recording this, just to announce this to colleagues, that we are recording this. So, uh, anyone that objects to this, please, maybe you shouldn't ask the questions or raise your voice. Thank you very much. So we started recording now. Thanks. Sorry, Anna.
Okay, no, it's fine. So let me talk then about the motivation of this paper. So the idea here is that there's a literature right now that kind of explains why credit spreads are important for macroeconomy. So the credit spreads are normally difference between corporate bond spreads and treasury bonds, and how they may affect the future of the macroeconomy. So when credit spreads are widening, which means that there's loads of risk in the credit markets, this has a negative effect on the economy. Uh, I have done some work before in which we actually look at how financial shocks may have different effects on macroeconomic variables like economic activity and inflation variables, depending on financial conditions, or depending on what you call in that paper credit stress conditions. Other thing we know, so if you see the title of my slide, I have actually the word monetary policy. So the link with credit measures, credit spread, and credit conditions in monetary policy is well done in this paper by Caldari and Herbst, in which they look at the impact of monetary policy shocks, and they claim that allowing impact at the time of the shock on credit is crucial to see the impact of monetary policy in macro variables such as output growth and inflation. And this is done because in this literature, the way monetary policy shocks are identified are with the aid of these high frequency proxies for monetary policy. And they're actually crucial in being able to disentangle this contemporaneous effect of monetary policy on credit conditions, because otherwise this is a very hard thing to do. Now, what we are going to do in this paper, what we do in this paper, is we wanted to see how the transmission and the impact of monetary policy on key macro variables, how they depend on credit conditions. And to do so, we're going to use a nonlinear vector autoregressive model. Okay, so the model is going to allow us to measure the impact and the dynamic effects for monetary policy varying across regimes, and actually to measure asymmetries. Now, the kind of nonlinear VAR approach we're going to be using here it's a kind of something that has an old tradition in macroeconomics. It's called smooth transition vector autoregressive models. The first time that was used in monetary policy was done by Wise in 1999. There's this famous paper by Warwick that look at fiscal policy shocks that use a similar kind of methodology. So it's something that has some tradition, but it's quite different from the most popular nonlinear models in macroeconomics, which are the Markov switching models. The main difference here between the smooth transition and the Markov switching, some of them is that when you move from one regime to the other, you do that in a very smooth way. So you build it up. And what happened with these smooth transition models is that, at each point in time, the dynamic transmission depends from a combination between the parameters of two regimes, and the weights are given for this thing that we call, the jargon is called the transition function. So it's different from Markov switching models. And one of the main advantages too is that what drives the regime changes is a combination of observed variables. So I can tell stories about what makes regime changes. Of course, you can do that with Markov switching too, but you normally do that ex post. Here I can kind of embed that kind of story within the model. Finally, again, this kind of model I've been using before to look at the impact of credit conditions long time ago by using the commercial paper spreads. The advantage of the kind of model we have is that we have this move transition and we can use a combination of variables. So if you look at the literature, people actually use the word financial condition index because they use many different variables to measure financial conditions. So the kind of approach I'm gonna use in this paper actually allow that kind of thing. So allow to be agnostic on how you measure credit conditions. So feel free to ask me questions if you wanted.
I think
So
there is no question for the
okay.
moment, so I assume everything is clear for the moment.
Okay, so let me keep explaining this then. Thank you. The other characteristic that we have in this modeling is that I kind of indicated a bit is that normally when people look at the impact of monetary policy shocks using vector autoregressive models, they normally look at a small set of endogenous variables. So it's like prices, output, you know, like a policy rate, and then probably credit spread. Now, some people do prefer to use large information sets. I'm not saying I'm not the only one that thinks that way. People have done that before with Bayesian VARs, in which you use shrinkage priors to be able to deal with dimensionality issues in VARs, because VARs are very parameter hungry. And also the inclusion of the use of factor augmented VARs also be used in the literature as a way to use information of many different variables to be able to identify the impact of shocks. In the VR I'm going to use in this paper has 20 endogenous variables, so it's reasonably large, and has 13 legs, so it actually has lots of coefficients. So we have 8 different measures of economic activity. So these are monthly series, so includes things like industrial production, unemployment. Has 4 measures of prices, so the different price indexes. To measure short rate, and this helps in the discussion on how you measure monetary policy in the times of very low rates, and 6 different measures of credit conditions related with credit spread. So it's a quite rich information set. So if you see what I'm talking about now, I told you I want to look at the nonlinear VR, and then now I just told you that I want to look at a VR that's reasonably large. So the question is, how is our strategy to deal with this dimensionality issue? Our strategy is this one I'm showing in front of you now. Is called a multivariate autoregressive index model. So this is something that's old in the literature. So it's from Rice 1983. So it's quite traditional. It's a reduced rank kind of VAR approach. But my co-authors have been working on this in a kind of Bayesian version and to estimate. So traditionally the model was estimating by maximal likelihood. So this uses a Bayesian estimation, and this is what we're following up in this paper. So the nice thing about this model is because there is a bit of a dimensionality reduction, what leads to is that we're going to have a small set of common shocks that's going to drive the dynamics of a large set of endogenous variable. And this is actually great for structural analysis because the number of shocks or what I need to worry about when I do identification is mainly the common shocks, which is a smaller set. It's much harder to do structural analysis with large VRs because of how you impose identification conditions. So the advantage here is that we're going to use these common structural shocks that are going to come natural from this modeling approach to identify monetary policy shocks using external instruments. So we're going to use the most recent approach to identify monetary policy shocks.
Sorry, Anna. So just a question. So so I guess you have a set of key variables, right?
Mm-hmm.
And then you have you have the controls, right? So I assume that you allow for a large number of controls, and then you use this sort of like maybe you can use principal component analysis to summarize them. Is that what you do, or?
No. This is a bit different. So because we start from the VR approach. So the VR approach is this approach that everything is endogenous, right? So you have a system of equation. You have one equation for each endogenous variable. So I start in a world that I have 20 variables, means I have 20 equations, one for each variable, and each one of them with loads of parameters to describe the dynamics of the across variables. So what this approach does is to impose restrictions on the dynamic across variables using these factors or these indices. Okay, so the existence of some common components on the dynamics of variables are going to allow me to do a bit of dimension reduction on the size of the matrices I need to describe the dynamics of the system. So it doesn't have control variable per se, but it has an issue of dimension reduction here.
Okay,
Potentially, I'm interested in all these endogenous variables. So I can compute the response to monetary policy shocks for all these 20 variables.
I see.
Yeah, is that clear? Yeah. So one of the things what we do then when we combine the multivariate autoregressive index with the smooth transition idea is that, of course, we look at the smooth transition multivariate autoregressive index model. And what this does is allow changes in the dynamics with regimes both in the conditional mean, which is the main dynamic to get the transmission of the shocks, and also in the conditional variance, which means that allows the variances of the reduced form shocks and the structural shocks to change with the regime. And because the way the dimension reduction here works is via factors, I'm going to explain exactly how it is. It's a type of observed factor. We're gonna actually use the factors to help us to figure out what the regime changes are. So the variables that drive regime changes are also one of the factors, and we're gonna choose based on fit of the model. Another feature of the model is that once we compute dynamic responses, the responses to shocks are gonna take into account the fact that once a shock hits the system, that may make the system to change regimes. This sounds natural here, but in the literature it's very common that the people estimate coefficients for regime A, coefficients for regime B, and then they treat this as if they're like completely different systems, and they never let the dynamics to mix again, and we're not going to do that. Okay, so we're going to take in serious the nonlinear dynamics of the model. And what's going to happen is because we do exploit the nonlinear dynamics of the model, I'm going to show you results that if you do monetary policy tightening or monetary policy easing, so if the Bank of England increase the rate from 1 to 1.5 or decrease from 1.5 to 1, this 0.5 change is going to be different actually. So the impact that easing and tightening have are asymmetric. And this asymmetry comes from the embedded nonlinearity in the model, because depending on the type of shock, the probability of regime changes. The model is going to be estimated using a Metropolis in Gibbs algorithm. So traditionally in this is a Gibbs sampling, and we need some Metropolis step for some of the parameters of the model. So the main contribution here empirically is that we do find lots of evidence of asymmetries related to credit conditions. And we find asymmetries on the size and the size of monetary policy depending on the credit conditions at the time that the monetary policy is done. And one of the main things we find is that in some periods of weak credit conditions, if you have what we call here, I call here decisive monetary policy, so basically you make the interest rate decline a lot, which is something you could do if you start in a reasonable level, then that could have effects on economic activity inflation that are large, disproportionately large than if you have done just a small easing or if you have done a tightening. Which means that, and the reason that this happens is because monetary policy, of course, affects credit conditions. So there's no linear relation between credit condition and monetary policy is what drives these asymmetries we find. Now, this is important because there's some other people that try to measure nonlinearities in the literature, but they don't have the kind of explanation linkage that this kind of dynamic system has. They would do in a more non-parametric way, or and in that case, it's a bit harder to see that kind of links. Okay, so I guess I'm going to move on if you have no questions. So I'm going to show you the equations now. Let me see if I can do something. Okay. So the first equation you see in front of you here is a VAR of order P. So it has an intercept A0. So you're modeling here, n variables. So you have one equation for each one, and they all link to each other. The number of legs is P. And normally the disturbance are assumed to be, multivariate normal with matrix, sigma matrix is a full matrix. Now, this model here, depending on the number of legs, it has loads of parameters in this matrix CU. Okay, so in my case, imagine that this CU is 20 by 20 for each P, and if using monthly data, you might want to use 12 legs, for example. So this is a very heavily parameterized kind of model. So the multivariate autoregressive index is a way to make this matrix CU here to be a bit, say, decomposed into two, AU and B0, where B0 doesn't change with the legs and AU does. And basically what B0 does is it can be written this way here in the bottom. So it can be written like a linear combination of the observables. So basically the idea here is that the matrix B0 has dimension R by N. So where R is smaller than N. So in my case, for example, R is equal to 4, which means you're going to have 4 of those factors here, which are linear combination of the observables. Okay, and this dimension reduction allows this AU matrix here to be much smaller than this AU matrix. There is some issues of identification. So in this literature, normally the thing you need is that these loadings here, B0, that you need at least one of the loadings per row to be equal to 1. And you're going to see that it's going to be natural in my application how to impose this restriction. This is basically what we do then. So think about this is the multivariate autoregressive index. This comes from ISO. And this is why we do differently. So what we do is that if you look at this part here, this is basically what we have in the previous slide. So this is the dynamic driven by the factors, okay, the linear part. But now you have a different part here. So this additional part is what I call the nonlinear part. Some people sometimes present this as the difference between two regimes or the coefficients of one regime and the other. So what DU measures here is basically the difference in dynamics between regime 1 and regime 2. And this difference in dynamics depends on this phi here. And that's the crucial thing on a smooth transition model. So the phi is this function that's here in the middle of the slide. So what this function is a logistic function, okay, that depends on a transition variable, which is in this case xt minus 1. So now I'm not going to keep with me to explain what this transition variable is. And depending on the size of this transition variable with respect to c, which is called threshold, and the value of this moving parameter, which is called gamma, this transition function is going to be very near 0, very near 1. Or can assume values in between. So when gamma is large, the transition functions kind of jumps between 0 and 1. When lambda is kind of medium size, it moves smoothly and has like the logistic phase shape. I'm going to show you this function soon, the one I estimate, and you're going to see that it's going to look very logistic. Now, xt minus 1 is actually going to be one of the factors. So there's a bit of a equation here that kind of says that I use one of the factors because there are factors. The only thing I do is that the way this model is estimating on monthly differences. So the data is very it's kind of noisy. So to get a regime changes, you probably need something that leads to regime changes, not to outliers. So what we do is we use the year-on-year growth rates, which is equivalent to the sum of the difference over 12 periods. So this is basically model dependent. It's because we use monthly data. Do we have any question about this slide?
Yes, we have two questions here. So we have one from Majid and another one from Shink. So maybe Majid, you can ask your question.
Yeah, so my question is about the identifying restrictions on the previous slide. I think, hold on a second. I think you need more restrictions than that, right?
So this is the ones I need. This is the one I need, but they're going to impose more. You're going to see. I'm going to have many restrictions on this B0. The B0 is going to be a quite sparse matrix. The reason I do that is because I need to then name these factors, and to do that I need more restrictions.
Yeah, I think you need R-square restrictions to get exact identification, because you can always multiply B0 by an invertible matrix and all the A1s by the inverse of that matrix, and you get equivalent parameters. So
I'm gonna show you. You say you need C. Okay, thank you for the comment. Need I-square. Okay. That is.
So the second question. Sorry, Majid, you have.
No, I was just saying thank you. Thanks.
Okay. Yeah, so the second question, I'm going to read it, but I think maybe you answered this before. So the question from Xing, a colleague, who he say is the dimension reduction method like a reduced rank regression?
Yes,
so that's his question.
It's similar to reduced rank reduction. The only difference at reduced rank regression, the B0 here is not B0. It's something that changes with the legs too. Here this constrained version is called multivariate autoregressive index, in which the one of the matrices doesn't change with the legs.
Does that answer your question, Xing? He said thank you.
Okay, thank you then. Okay, so this was kind of the crucial slide, which is the model we propose. There is one more thing I should say about this model, which is the regime changes also affect the variance. So the variance of this reduced form shocks or disturbance also change with regime and change exactly with the same function. So in the upper regime, in the lower regime, they're gonna have different variances. So the way we model the time variance is very simple and intuitive. So you have two of those, sigma 1 and sigma 2, and at each point in time you're weighting those two matrices using this the transition function. Okay, so that's the idea. So the variance changes with regimes. Okay, let me talk more about identification and how we get the responses.
So why you don't have the same expression in the mean? Possibly you explained that, I missed that.
Just because you see, you could write this way. This equation here is just that I like to write this way with the linear part and the nonlinear part because it's the way I estimated. But this way of writing is equivalent to this one. So du here is the difference between the coefficient on the second regime and the first regime. If I write this way, if I write, in this way here, then you have, the coefficients of one regime and the other. It's kind of the same.
Okay.
Okay, let me talk then. This is crucial because remember, I want to do monetary policy shocks, right? So I need to think about identification. So first thing, the question about the factors. So let me explain how B0 is. So B0 is actually full of restrictions, and I need to think more about this R2. So this is the set of variables we use in the model. So I kind of divide the set of variables into groups, say. So you have the activity group, which has A variables, is here, and then you have this inflation group. We have the variables there with CPI, PPI, PCE. Short rates, we use the Fed funds, and so during the period that the zero lower bound, it uses the shadow rate, and we use the 1 year rate. Actually, most of the papers on monetary policy recently have been using the 1 year rate to do analysis because of the zero lower bound. And this is the credit condition variable. So there's commercial paper spread. This is excess bond premium is a measure computed by Zakraev that's very popular. BA spread, mortgage spread, TED spread, and term spread. Now, I know that the term spread is not the same as the other ones, but in here, actually, B0 is going to come with a negative value. I mean, some credit conditions do use term spread. It's just that it loads in a different way. Now, the restriction we impose here in the end is the following. So the first variable in each group has a loading equal to 1, and only the variables in that group have a non-zero loading. So in the end, we do impose loads of zeros on the B0 matrix. Okay. Now we did some work trying to figure out whether the variable that we decided the loading was equal to 1, if that matters. For the case of the credit factor, does matters a bit. There's some scale point there. And we actually use the order that you have in front of you here. So we look at fit to figure out. And remember, fit here, because this is based on estimated, it's based on the average likelihood over the posterior draws. Okay, so this is the restrictions on B0. This is how the factors look like on the model. So we're going to have 4 factors because of the 4 groups. The data has been normalized so that you see these things move around 0 here. So the blue line is the activity factor, the black line is the inflation factor. The interesting thing about the activity factor is that it's highly correlated with economic conditions index. So what you see as blue here, it looks like the US business cycles. This is the other two, which is the short rate and the credit factor. So the black line here, which is the credit factor, which is again is estimated within the model using the restrictions I put in the matrix B0. It looks very much like has a very high correlation with the Chicago Fed financial conditions. So what we have in here are things that are easily identified. And if you notice, some people when look at factors, they think the factors should not be correlated, but this type of factors, they are. You can clearly see that the black line is correlated with the blue line, okay, which is the short rate factor. Okay, so
before you move on to the rest of the equation, there is a question again from Majid. Majid, can you?
Yes. So so how did you come to the number 4 as the number of factors?
Okay. In the paper by my co-authors, they actually have a way to figure out the number of factors using the marginal likelihood. In this case, I basically kind of decide for economic reasons to have 4. I could have used the marginal likelihood to decide the number of factors on the multivariate autoregressive index model, but within the nonlinear model, it's much harder to do because I cannot compute the marginal data density in closed form solution. But in multivariate autoregressive index, you could do it.
I see. Thank you.
Yeah, but you have a point there. You need to decide the number of factors. Okay. Next step is the following. So there's something about this model that if you multiply the smooth transition multivariate autoregressive index by B0, you get a kind of VI in the factors. And that's basically what you have in front of you now. Now, the interesting thing about this VI in the factors, you see you have F here and F here, is that these U's here are basically linear combination of the old disturbances. Okay, and of course, because of the dimension reduction, what's going to happen is that the number of shocks you have here is much smaller, is R. So in my case, it's going to be 4, which means that this kind of shows that in the end of the story, you kind of have 4 common shocks driving the dynamics of the system. So I'm showing this now because the way I'm going to identify the impact of monetary policy shocks is actually using these common shocks, common reduced form shocks. Okay, so I'm going to start with this UT, which is a linear combination of epsilon, to figure out how I'm going to carry out the identification. So let me show you what's the idea here. So as tradition in the literature, I have a vector of reduced form shocks, and I assume that they are a linear combination of the unknown V's, which are the structural shocks. Now, the difference between the reduced form and the structural shocks is that the structural shocks are not correlated with each other, and the reduced form are. Okay, which means that this VT here, you know, they have diagonal metrics, and here I apply the usual normalization, and I assume that they have a variance equal to 1, which means that they are going to be looking at 1 standard deviation shocks based on this. Now, the whole story here is how to define this matrix HT. So here I'm going to be looking at just one of the columns of this matrix. So I'm going to do partial identification. I'm going to be interested in just one specific shock, now not the 4 of them. So I'm going to be looking only at identification of a monetary policy shock. Okay. So you're going to be looking at this column vector here. And this is what we're going to look at the next slide. So the idea here is that they're going to have, so this column vector is going to give me the impact effect of monetary policy, and I'm going to assume that they can have one for each regime. So if you see here, I have HT, so it looks like this is going to be varying over time. And the way it varies is that it's basically constant across regime 1 and constant across regime 2, but those two things could be different. Okay, and the way we're going to do this is the following. I'm going to use the Jerton-Karady external instrument approach, which comes from another paper by Morton Harvin, actually. which basically the idea is that to compute this matrix H, I do a regression between the common shocks on the shock of the short rate, but instead of doing a regression by least squares, I do two-stage least squares in which I use the proxy variable as an instrument. So what H gets is this exogenous variation that links the reduced form shocks to the reduced form shock on the short rate. Okay, and by doing so, I can estimate H. I also need something else to estimate H. I need to take into account some scale effects. And when I do so, then I use the variance that's regime dependent. So remember, I have one variance for each regime. So I'm going to use that. So H here is going to be different across regime because of the size of the shock is different. But in terms of identification, so in terms of elasticities on how one shock affects the other variable A or affects variable B, this is going to be on average over the full sample. Okay, because otherwise my results would look quite different from the ones in the literature, and I wouldn't know why. So we're going to be using two proxies. So in the literature of monetary policy, there's some discussion about which proxies to use. So remember, these proxies as things that are correlated with the monetary policy shock, but are exogenous variation of monetary policy. Okay, so they're correlated with the residual of the equation of short rate, but they drive exogenous variation. So it's not a variation that is related to macro variables, but it's something completely exogenous. So I'm going to use proxies from two papers. They are based on high frequency data. So they're basically on how future markets react to monetary policy. The difference between Gert and Clarade and Miranda, Agrippino, and Enrico is that Miranda, Agrippino, and Enrico remove some of the variation of the original shock because they think that some of it is not unexpected monetary policy. Some of it is just markets reacting to the information in the forecast of the Fed. And when they do that, the shocks look a bit different. You're going to see that my results would change depending, in some cases, with the proxy we use. Okay, so I think there's advantages in identifying these on the common shock. So there's no issues of misspecification on the VAR, on the factors. And you have the advantage that we can use many different measurements because the factor per se measure economic concept. So this is a bit agnostic on how you measure activity, inflation, and the short rate. Okay, so this H matrix here is basically based on this thing, on the VAR, on the factors. Okay, so basically I'm identifying the impact of the shocks on F. But that's not what I want, right? I want the impact of the shocks on all the 20 endogenous variables. And this is basically what this slide here is about. Okay, so it's the VT, which is basically the structural shock on all the other variables. And here I have this YT plus 1 because I'm just looking at the impact. So time T plus 1 is the time of the impact, okay? So you can see I have the same matrix as I had before, and then I have a bunch of matrix being multiplied by each other. So that thing comes from the fact that there is a decomposition done for multivariate autoregressive index that you can say that the reduced form epsilon t can be decomposed between the common shock and the schizacity, which are idiosyncratic shocks and are orthogonal to UT. So basically, I'm kind of saying that only this part here is the part that matters because I'm identifying the common shocks, and these idiosyncratic shocks don't matter and don't mess up my identification because they're supposed to be orthogonal to UT. So this comes from the composition. So this allows me to get the impact for all the variables in the system. Okay, so if I was fine, Anna, yeah, interrupt me now.
So these impacts are they conditional or unconditional? I mean, do you condition to the state?
They are conditional on the regime. So you can see when I have this reg, it means that whatever that matrix or that vector is changing with the regime. Okay, so you can see that some things are not, like B0 is not. This one is going to change due to scale. So the main reason here why the impact changes is because I have that variance and covariance changes with regime. That's the main reason.
But yeah, but then I mean, in practice, I mean, okay, I mean, okay, if I think about, like, you know, like the literature on Markov switching, etc. So the state is not observable, right? I mean, the state of the economy. And then, of course, you cannot condition on something that you don't observe.
So here, remember, the idea is that first you kind of estimate the model, and then based on the model, you compute these responses, okay? So, of course, I need to take into account parameter uncertainty to do so. So I'm going to take into account the fact that I need to estimate the regimes, if you want to think about it. But once I do this, I can use the current estimate I have with the current set of parameters to do this computation, okay? So conditional on a set of parameters of the model, I'm going to use the history of the regimes to do this computation.
Okay.
Maybe this is going to be clear.
Yeah.
This
So
is
you
going to be clear
condition
when
to
I
the
show you
state.
the results. Yes.
Okay, fantastic.
I might show you the results soon. So this is another slide that just says how I get the dynamic transmission. So the impact is just up here. The dynamic transmission bases the difference between two paths, one path with the shock and one path without it. So what I describe is the impact of the shock at time t+1. For the ones from t+2 up to h, which horizon I wanted, the way I do is that I simulate it. So basically you need to compute the expected value of all the endogenous variables conditional on having the shock, which is omega here, and conditional on not having the shock. And you can see that this condition on something else, this IT, which is the information available at time t. So the idea is that you compute this response here for each point in time. So you have one response at each observation in your data set. You need to depend on H, which is the horizon, and of course the shock identification. To be able to compute this conditional means you need to do simulation, but I do based on the assumption of normality of the disturbances. So this is probably the story
you cannot do
me.
it sort of recursive. You cannot do it like recursively, or you may possibly end up having a
no. You cannot do recursive because the model is nonlinear. So I cannot. Because in the VRs, you kind of solve these conditional expectations here using by multiplying the matrices, right? Here I cannot do it because of the way the shock gets in the system.
Right. Okay.
Okay, so this is probably what you were asking me before. So the way we do is the following. So this is arbitrary, but this doesn't affect too much the result. So my transition function has values between 0 and 1. So I basically assume that I separate the two histories. So here I'm kind of computing one response for each point in time. So instead of showing to you all these responses, I'm going to split them in two groups, regime 1 and regime 2. And this is actually helps to get identification too, is between regime 1 and regime 2. And the way this is splitted is basically using the estimates of the transition function and get the ones that are very near 0 and the ones that are very near 1. I could put a threshold of 0.5 here. Some people think this is better or worse. I don't know. It doesn't make loads of difference. I'm going to show you the transition is really smooth, so that removes some histories, but most of the results are robust to small changes here. So in the end, I'm going to show you responses for each regime, which are going to basically be average over the histories of each regime defined by the story I just told you in the top.
Sorry, Anna, to ask another question here. I mean, so is there any implicit assumption here? So when you look at, let's say, long horizons, right? So what that means? You assume that the state is the same, or the regime stays the same?
So this thing here is actually crucial. So of course the system is stationary. So I hope at long horizons is not going to behave badly. But the important thing here is that you know, with the horizon, the difference between the expected value with the shock and without the shock may get quite different, because if there was a shock, it might be that a part of the system goes one way and the other goes another way, and that explains why sometimes and that affects the probability of regime changes. Something that I forgot saying is that when I simulate the model here, so this is the transition function is at a specific regime at the time of the shock. But as the time passes and the shock hits the system, I allow regime changes. So every time I'm doing the simulation, I'm recomputing the transition function, it might be you move to one regime and another.
Okay, that's my point. Okay, I got it. Yeah.
I'm going to show you, maybe this is technical. I have 20 minutes. I think I'm going to start showing responses. So this is some technical details. So something I ignore completely is that is parameter uncertainty. So all these responses are computed for safe draws of the posterior density. So when you see the bands on my responses, they do take into account parameter uncertainty of all the parameters in the system. Okay, all the dynamics, all the sigmas, all the gammas, C's, everything. Okay, this is basically how I'm gonna measure symmetries. So in the model, in a linear model, everything I'm saying here doesn't matter because if you have a VAR, you do a shock of +1 or shock of -1, one is symmetric to the other. Okay, so if you sum the response of the positive shock and the negative shock, you're gonna get 0. In this model here, I'm gonna use this kind of analysis to see if this is not 0. And the way I'm going to do is I'm just going to flip the impact effects I estimated with the external instrument, or I'm going to multiply that for something to try to figure out first this one, if it's monetary policy easing and monetary policy tightening have different effects. And the other one is the one that is in the bottom here, is in terms of the size of the shock. So whether 4 standard deviation shock has the same effect as 4 times the impulse response of a 1 standard deviation shock, which is basically what these kind of equations kind of tell you. Okay, and the way I'm going to try to get bands for this is using the fact that, again, I have the safe draws of the posterior, so I can compute these asymmetries for all the posterior values. Okay, so this is the estimation. Is there some Gibson? So the estimation of this model is not very slow, it's reasonably fast, and thanks to some tricks in the Bayesian VAR analysis. Okay, I have 15 minutes, so let me show the results because I think it's more interesting. So the yellow line you have in front of you now is the credit factor. So we're going to use the credit factor to deliver regime changes. These are actually in the paper, I show some results on using different transition variables, what happens with the fit of the model. And this is the case that fits better using the average likelihood. Then if you see these black lines here, so this thing here is the transition function over time. You probably cannot see that there are some very narrow intervals around. So this is the posterior mean, and it has very narrow intervals that are the 68% bands. So basically what you see is that the regime in the top here, it's quite prevalent in the 80s with some exceptions. And then you go to the bottom regime here, and then you have the upper regime back again before this recession. So this is US data in 2000, 2001. And then here you have the regime 2 again, while in the 2007, 2008 recession. So basically, you know, the upper regime is associated with recession, but of course covers a much larger number of observations in recessions. So this is not really a business cycle regime, okay? It's probably something else. But the periods here that you're in the upper regime are periods with weaker credit conditions, and periods here you are in easier credit conditions. So this is the response over time. This is the response across values of the transition variable. So this is the logistic function, basically. So here you have possible values of the credit factor, and actually here you have data points. I showed this to show that whatever are my estimates at the posterior mean, they clearly give me a gamma parameter that I have many observations here between 0 and 1. So this transition is very smooth, okay? Because so this is data points. You can see that there are more observations here, which is in the lower regime than in the upper regime. Okay, by the way, these things are spread around. Okay, so this is something else that's important too. So I told you I used 2 proxies for monetary policy shocks. So they are basically the orange line and the blue line in these slides. And interesting, I put also a gray line there, which is my kind of regime changes. Just try to see if I could see something. You can see that the variation of this proxy is a bit higher when it's in between these gray lines. So it looks like in the upper regime, the variability of this proxy is higher, which is a good thing, because one of the things that my estimate shows is that the variances of the upper regime are normally higher than the variance of the lower regime. So this kind of says that this may have hope of being a good instrument for the reduced form shocks. Okay, so remember, I'm going to use this to identify the impact of the shocks. So GK is Gatlin Caradi, MAR is Miranda Agrippino Enrico. They are based on the same thing, it's just that one is cleaned by information coming from forecast and the other doesn't. You can see that they are over a sample period between 99 and 2012. So I'm going to use this sample period to estimate the impact effects, although I use the full sample to estimate nonlinearities and actually to compute the impulse responses. There's a debate in the literature on how do this not in a two-step estimations tool altogether, but if I do here in this case, I would have a much shorter sample period, and of course to find nonlinearities in regimes is much better to have a longer period. So that's basically how we do. Okay, so this is the first response. So basically here what you're seeing is responses to the factors. Okay, I'm not showing responses to I, I'm showing responses to F. Why? Because it's actually easier to see. And remember, these factors, they are a combination of a group of variables. So for example, here you have the response of the short rate to a monetary policy shock. So you can see that the shock is about 0.10. So the scale of the shock here, it comes from that sigma matrix. So it's reasonably small. And you can see that goes down and goes back to 0 after, I don't know, a year. Here you have the response of credit spread. You see the credit spread jumps up with monetary policy. So this is basically what the external instrument approach does, allows you to do that. And then the impact effects here on price is negative as expected. The one-on activity with these proxies is annoyingly positive. If you look at the literature, that's basically what happened in Garrett and Caradi. But over time, it gets negative. So over time, the activity goes down with a tightening of monetary policy. Okay, so there's a comment here in the end of the slide that kind of says that I compute these responses for the factors, but I actually use the full system first. So I compute the response for the full 20 variables, and then I get the factor responses, just to say that I get all possible uncertainty here. And I press the wrong button. Hold on. Okay, I'm here. Okay, so these things kind of look fine. This is the same thing, so same picture as this one, just it has a different proxy. Now, the nice thing about this proxy, and that's why these guys wrote this paper too, is that the impact effect on the economic activity is actually not negative at impact, not positive at impact, is negative. And then, you know, so people like this more because it looks like activity variable behaves better as it should be. The other difference you find is that with this proxy, the impact that monetary policy has on credit is a bit smaller at impact. Okay, so you can see that everything I'm showing you here that's similar to the previous literature is computed during the lower regime. Actually not doing the lower regime, is computed at the lower regime at impact and allowing for regime changes over time. But if I do for the upper regime, things are quite different. Okay, so the difference in regimes is between this one and this one. And you can see that the main difference here on the short rates is that the rates goes down much faster. There's a stronger response on the credit spread, but that's because of the relative variances and covariance. And annoyingly here, the economic activity goes down in the beginning, but then kind of reverts and has these very big buns. For prices, you still have prices going down. So this response here is quite different from the ones you have before. Okay, so there are clear some difference across regimes. But this is what I think is more interesting.
Sorry, so when we look, I mean, the confidence intervals are quite large.
Yes,
and
yes.
Looks like these effects are not.
You can have a. Yeah. So you can have another interpretation here and say that so I'm going to show you some more evidence. So there is significant evidence of asymmetries, but I'm going to have to qualify that soon. Okay, so if you keep with me, so here you can see that in the upper regime, because the variance is higher, then you have this more imprecise, say, transmission, in particularly for economic activity, not much for prices. So what I'm going to show you now is evidence of this which if you have here, actually in this picture you cannot see, I need to show you a table in which in the upper regime, so in a shock that started upper regime, if I do monetary policy tightening or easing, you can see that the shapes of these responses are not the same. And I'm going to show you some evidence that in some cases you do find some differences here that are statistically significant, in the sense that even with these big bands, in some cases you find differences. Okay.
Okay.
So I see your point there. Although you saw that the shapes of the responses are completely different, right? So actually something that's hard to see here is because I do lower regime and upper regime, one after the other, you don't see that the scale of these plots are completely different. So if you put them in the same scale, you actually think that the lower regime, nothing happens because the upper regime things are so much more volatile. So there's a scale issue too. Okay, so let me go to this one. I think this is something important I should spend time explaining. So let me tell you what you see in front of you. So you have responses at horizon 24, 2 years after the shock. It's just arbitrary horizon that I thought was different. And the numbers you have, I don't have bands here, but I'm going to show you bands later. So this is the numbers at the posterior mean numbers I showed you before. So the idea here is that you have tightening policy and easing policy, okay? And they're done starting in the lower regime or started in the upper regime. Now, if these things are symmetric, you have something like here. You see the response of activity is minus 0.7 and the easing is 0.6. It looks kind of very similar. Okay, you can see that these numbers here kind of very similar to each other if you take in absolute values. But in this side here, when this same kind of policy happens during the upper regime, you can see you cannot find a symmetry anymore. I mean, it's 3 against minus 0.8. Those things are actually in the same sign. They're supposed to be in opposite sign if they were symmetric. So you start seeing some evidence here of asymmetry. Now, these numbers here, the probabilities of being in the upper regime is what I use to explain that. So the idea here is the following. I have a tightening or easing shock of 1 standard deviation happening in the lower regime, and there is very low probability that the tightening will make you move to the upper regimes. There is a 7%. If you do easing, this probability is even smaller because you know, you're easing conditions, right? So you're likely to stay in the regime of good credit conditions for even longer time. But the interesting thing here is that the upper regime, the difference of these probabilities here is much larger. And that explains why you can find more evidence of asymmetry there. So if you're in the upper regime and there's some tightening of monetary policy, you're going to stay in that regime in 82% of the cases after 24 quarters. If you do this, the easing instead, so it's the same shock, you just flip it, then you're going to stay in the upper regime only 66% of the cases. And this difference kind of justify why in the end I find evidence of asymmetries. The asymmetries depend on the proxy, so the JK proxies where the effect on credit spread is stronger, you find more asymmetry, which is natural because it's the credit conditions that are delivering regime changes. There is a next table which show the same thing, but instead of 1 standard deviation shock, a 4 standard deviation shock. When I started doing this, I thought, I'm crazy. This is too big a shock. It's not realistic. But actually, in some papers, people do use this 100 basis point shock. I mean, it's more common to have the 0.25, which is like the one I had before. But there's, in particular, there's a recent paper that uses 100. Now, if I do that, I have much bigger shock, which means you can see that the difference in probabilities here in the upper regime between easing and tightening are much larger. So if you do a large easing shock, you're very likely that after 2 years, you're going to be to the lower regime. So you will switch regimes. If you do a tightening shock, then you're very likely you're going to keep in this bad regime here. And then you can see that the responses are then really quite different. And you can see here actually that the easing shock leads to very high growth on activity and prices after 24 quarters in the upper regime. See these numbers here. Hold on, let me do something else. So this 8 here is quite different from these 2. So the difference between these numbers is the following. Here is basically the impact of easing starting the upper regime after 24 quarters, so make GDP growth increase a lot, and of course inflation increases too. And this is basically the same shock. It's just that instead of happening during the period of weak credit conditions, it happened to the period of good credit conditions. So you can see it has a much smaller effect on activity. So, and then the reason here is because you're already in this regime here of good conditions, and you're not going to leave it. So this explains as well why there are these. You see here that the difference across regimes look much bigger. Okay, some responses. I should be finishing. So this is the visual aid for the asymmetries. So you can see, for example, this is the kind of symmetric responses. So if you have, so the credit responses are very symmetric, but you can, here these ones, so the gray line here is easing and the black line is tightening, but you can see in the economic activity, those things don't look very symmetric, okay? Let me think, what should I do? Let me try to see. I know this is a very big table, but this is actually the evidence that the asymmetries are significant. So maybe I should show. So what you see in front of you are actually bands, 68% bands, and the ones in bold means that they don't kind of include zero in these bands. And the bands here compare cases of tightening and easing. So if these things include zero, means that the shock is symmetric. When you have a small shock and when you have a large shock, and when you have 4 times the shock, the responses when you have a shock of 4 standard deviations. And basically the bits in bolds are the case that I do find evidence of this kind of asymmetric effect. There is more of JK proxies than with the EMIR proxy because of the impact that proxy makes the monetary policy has on credit. And an interesting one you'll find here is that you have things like this, which kind of tells me that a large easy shock has a much stronger effect. Sorry, I need to read here because otherwise I'm going to get confused. So a large easing shock has a smaller effect on activity in the upper regime, but this thing here means that it has a stronger effect on the prices in the lower regime. You need to think about it because these asymmetries are a bit confusing. Interesting enough, this is exactly the same result as Barnishon and Mates using a non-parametric way. But the advantage, I think, of the model we have here is that I can explain why that happens. So it happens because you have this nonlinearity between monetary policy and credit conditions, and the asymmetry is driven by the fact that the regime may change after the shock, and the probability of regime changes after the shock varies with the type of shock and with the regime you are at the time of the shock. Okay, I think I'm going to stop talking in case you have additional questions.
Right, so yeah. Any question?
Otherwise, I'm going to keep talking.
Yes, so I think it's quite, it's quite clear. So, I mean, for the last table, I mean, the numbers are very, we can see that these numbers are very different, right? I mean, in terms of capturing this, asymmetry. But I'm wondering whether you can test that.
You see, I'm being. I shouldn't basically use the word significant as much as I did, but what I did is, you see, at each draw, I compute both cases and take the differences, right? Which means that across all draws, I have the distribution of the differences. So it's a kind of empirical distribution, if you want to think that way.
Right.
And then I look at it to see if in the 68%, again, you can complain about my 68% as much as you want to, and I'll use 90 or something. I can look at if in my interval, if I have 0 or not. So it's not really testing, if you want to be fair,
yeah.
But it's a way to consider whether this, even with all the parameter uncertain I have, which is a lot because I estimate loads of parameters, whether I can find any supportive evidence based on the data I have.
Yeah, maybe there is a way, because I mean, because so that's about comparing the impulse response functions, right? And maybe there is a way to have. So these impulse response functions, they come from different models, right? That's correct.
No. They are within the same model. So the only difference they have is that at the impact. So basically, the only difference between these responses is basically that impact.
Yeah.
The H matrix is a bit different.
What I'm saying is that, you know, the
H matrix is
so one comes from when I say different models, I mean you have restrictions. You put some restrictions. Is that correct?
So
In one,
so what is varying here in the bands is really the fact that the parameters of the model have a density, right? So the bands of the responses and the bands of the asymmetry, it comes from the parameter uncertainty of the model, if you want to think that way.
Oh.
That englobes all the assumptions I did.
Okay.
On identification,
anyway.
On the dynamics, on everything.
Okay. Right.
I hope this was clear. If anyone wants to comment, it's all fine.
Yeah. Great. I think it's quite clear. So as usual, you know, a little clapping on behalf of my colleagues. So we do that.
Thank you.
We do that at the end of all our seminars. So given that there are no more questions, so again, thank you very much, Anna, for accepting our invitation and for the great presentation. And as I said, so hopefully when this crisis is over, we'll be more than happy to have you visiting us here physically.
Okay. Thank you.
Thank you very much, and stay safe. And thanks a lot for all colleagues who attended this this presentation, even though it's a marking period. But thanks a lot again for.
This is a relaxing from marking. Anyway, I can stay 2 more minutes if someone wants to ask me an informal question when you stop the recording. Maybe people want to ask more.
Exactly. Let me see if there's okay, so there's no question. Oh, there's a question. Okay, Majid wants to. Sorry, I didn't see your question, Majid. Do you want to ask your question, or?
No, it was already answered.
Oh, okay, great.
Yeah.
Sorry, I didn't see that.
That's
so
right.
Again, thank you very much, everyone, and so stay safe, and thanks a lot again, Anna. So hopefully we'll see you soon in Durham after this this crisis is over. Thank you.
Thank you, Anna.
Thanks
Take care.
Bye.
Bye. Okay, I'm gonna get away. Okay, I think I'm gonna